Okay, greetings to one and all. This is the SNIA, the Storage Networking Industry Association. This is a presentation on storage for artificial intelligence applications. And a few tips for all of you to begin with. This is going to be a lot easier for you if you go full screen and zoom in to where you can see things. There are some slides where the print gets rather small, so that will be a useful thing for you. When we get to the end of this talk, please give your feedback. As you sign out, there will be this little questionnaire for you. Give us your feedback. Let us know how we did, what we could do to make it better. Do we need to do more presentations like this? Those kind of information, that's very valuable to us. Keep your questions for the end, or ask them along the way. Just do that in the questionnaire window. We will answer them at the end, and those that we don't get to, we will answer afterwards. And all those question and answer things will appear in our blog in about another week. So today's presenters include myself. I'm the moderator, and we'll begin with our presentations with young Paik, who's the Senior Director of Product Planning at Samsung, followed by Brien Porter, a Solutions Lead at Intel, and closing us out before we begin the roundtable presentation will be Craig Tierney, a Principal Product Architect from NVIDIA. So SNIA, who are we? Well, we're 180 different organizations within the high-tech industry. There's over 2,500 active members, and we provide material to over 50,000 end users and storage professionals around the world. To learn more about us, there are links here. Let's see. We cover many things, many different bits of technology, from Ethernet, fiber channel, InfiniBand, iSCSI. We go through all kinds of things about securing protocols for storage, securing the data underneath the storage. How do we deal with virtualization for storage? Many different technologies all around the technologies of storage. Of course, it wouldn't be a presentation if we didn't have something from the attorneys. The material contained in this presentation is copyrighted by SNIA, unless you see otherwise. Member companies and members may use this material in presentations and literature only if you reproduce it in its entirety without modification. And of course, SNIA must be acknowledged as the source of the material. This presentation is a product of SNIA. Neither the author or the presenter is an attorney. And nothing in this presentation is intended to be or should be construed as legal advice or an opinion of counsel. If you need legal advice or a legal opinion, of course, contact your attorney. The information presented herein represents the author's personal opinions and current understanding about the relevant issues involved. The author, presenter, and SNIA do not assume any responsibility or liability for damages arising out of any reliance on or use of this information. No warranties, of course. So today's agenda will begin with an introduction to data science, then cover data and the artificial intelligence life cycle, and the mapping of business questions to the different types of AI algorithms. Then we'll do a discussion about model training and data usage, followed by the roundtable Q&A, where you'll see all of us instead of the slides. So now I will hand this off to young Paik, who will begin the presentation.
Hi all, this is young Paik with Samsung. To start with, I wanted to kind of give a little bit of a lay of the land And so we'll start by saying that data science is a broad field that covers everything from data cleansing, preparation, and analysis. It involves statistics, mathematics, programming, and creative problem solving to extract information and insights from data. When an accelerator is used to improve the performance of data science workflows, we call this accelerated data science. Data analytics, machine learning, and deep learning are widely used approaches to solving problems in the field of data science. This has been around for a long time. It's used to examine data sets in order to draw conclusions about the information they contain using correlation, statistical modeling, and other methods. Machine learning uses statistical techniques to construct a model from observed data. It generally relies on human-defined classifiers or feature extractors that can be as simple as a linear regression or the slightly more complicated bag of words techniques that some of the first email spam filters made possible. Deep learning is a machine learning technique that automates the creation of feature extractors. And we call this feature engineering, using large amounts of data to train complex deep neural networks, or DNNs. So DNNs are capable of achieving human levels of accuracy for many tasks, but they require huge data sets and tremendous computational power to train. Several years ago, researchers started applying DNNs in a variety of areas and are reporting amazing results. This has precipitated the modern era of AI as we see it today. So most of the talk that we're going to go through, I just wanted to focus on the deep learning aspects, and some of this will also apply in general to machine learning, but we wanted to make sure you understood we were talking about a specific topic within data science. So next, let's take a look at how you design data storage services. What does the platform look like? As the performance of the compute elements for AI continue to increase, the need to get that same performance increase from storage is there as well. Let's take a look at some of the considerations. And not all of these will be applicable for every use case. So don't hold me to this for everyone. Let's first take a look at storage intelligence. And these are different techniques for kind of minimizing the cost of the storage. And they include things like thin provisioning, which allows you to use and pay for only as much storage as you need. Deduplication and compression reduce the cost of per gigabyte of storage. Encryption also helps you keep your precious data very safe and away from the eyes of harmful people. There are a number of ways to optimize data internally as well. And one of the critical factors is how the data is organized. Is it tiered across different media, hard drives, SSDs, DRAM, etc.? You might have the data in different locations. You might have to move them. But simple economics says that you should store the data that you need most on the highest platform and reserve the lower platforms for things that you don't need quite as often. In my experience, automation is often an overlooked area. It's absolutely essential for the long-term stability of your system to make sure that you have the right automation in place. A very big consideration is to look at not just how much storage you need today, but how it will grow. If you take a look at these architectures, in general, you want things that will allow you to scale out, right? Don't just scale up in a big monolithic system. For some people, this means a hyperconverged infrastructure will work fine. And for others, they might need to use some form of software-defined storage that's a bit different and allows a different level of scaling. This will depend completely, again, on your use cases. And then there's orchestration. These are the technologies that allow you to integrate and manage disparate systems that hold and manage your data. We live in a world where we still need to attach to legacy systems, and we will have to incorporate those into new usages. Okay. Now, we should take a look also at all the different types of use of storage. And this chart kind of illustrates what I'm talking about. And a question that I'm often asked is, do you need to actually take a look at all of these different kinds of storage and make use of them all? You actually might have to make a lot of use of the data where it is, and in some cases you might have to move it. But they can sit pretty much anywhere on this chart. And so if you take a look, they will range from simple data services all the way to very complex ones. You might have OLTP databases are in effect. And the performance of these systems will be quite different as well. Some of them are meant to hold massive amounts of data, and others will hold them in maybe smaller amounts of data, but definitely you need higher performance from them. And this kind of shows a big broad swath of all of these things. You might find yourself trying to read log files coming from different systems and simultaneously accessing an OLTP database to train a model. You may also find that accessing an online OLTP database is very dangerous and decide not to go that route. I've seen some people take periodic extracts from the database in order to use that extract instead. This could be in the form of another database or just a file extract. In any case, you have to make up your own mind as to how you organize your data. But in general, it's best to minimize the amount of data movement so that you don't have to constantly be copying data and running into performance issues just because of that. Now I'll hand it over to Brien, our next speaker, to go over some of the different use cases. Brien?
Great, thanks, Young. So when we talk about the AI lifecycle, what you're looking at is how you're going to run your AI project. And as coming from the storage world, you want to be involved as soon as is possible as you go through, as your business goes through the process of defining the challenge, figuring out kind of what your approach is, and putting together the expertise. You want to make sure that you have the opportunity to work with the data scientists, work with the engineers, because as you define what the data sources are, where data is coming from, and you're going to need to talk to them about where those data sources are pulling from, and if that storage isn't going to work, what type of movement. When Young talked a little bit about things like data tiering, you're going to need to move some of that data to faster data sources. You're going to need to know what of your data is real time versus what of the data is going to be done in batch, right? As you're doing training, you're generally doing more batch work. As you're doing inference, right? So as you're actually making those predictions, you're doing things in a faster manner, not necessarily real time, depending on your use case. So you're going to need to figure out the philosophy. As a storage professional, it's really important to be able to talk to each of those. And we switched out of. As a storage professional, you're going to need to be able to kind of talk to each of the teams and figure out kind of the level of security they need for their data, who needs to access the individual pieces, where the data sources are, and what is the need for that particular data. From that, you'll build the infrastructure, and you'll put together the organization to make it work. It is very difficult. Making sure that you and your team are working together is a process, but starting from a strong foundation with a good architecture is always the best way to approach an AI project. So let's talk a little bit about the understanding kind of the overall workflow, right? So your data is coming in, you're going to go through a process of data discovery and pre-processing. From there, you're going to do your feature extraction. Generally, with AI, something like 70% of AI is actually ML, right? 30% is deep learning. So it's important that you're working with the data science team to look at what they're doing and how it needs to happen, and putting together a good plan. From that, your feature selection, pattern mining, data transformation, to eventually to your model development. And from model development and evaluation to your model testing, right? To make sure that the models that you have are working and are giving you a level of accuracy that is what you need for your particular solution. 5 and 6, that model development and model testing, that's actually a somewhat iterative loop, right? You're going to keep going through that until you get the level of accuracy that you need. In all of this, something to remember in AI projects is that once you're complete, that just means that you're going to kind of start the whole process over, and you're going to keep iterating on your AI solution, right? Both for the training part and for the inference part, as new inputs come in, as more data is evaluated in your environment. Let me send this over to Craig.
As we talk about, okay, so we've talked a little bit about machine learning from a high level and data science from a high level and deep learning from a high level. What are the types of questions we can start to answer using these algorithms? What can we do with our businesses? And so that relates to the types of models that we're going to use, and it relates to the types of data sets we're going to use. So for example, from a business perspective, if I wanted to ask the question, is something present or not in an image? So that already leads to the idea of that it's going to be a detection model. There's ways that can be done as an AI or DL task, and places you would see that it would maybe be cancer detection in healthcare, or potentially looking at cybersecurity when it's more textual data in terms of what's going on, like in terms of fraud detection. We have other types as well, like it's not just is it present, but what is it? So let's say you're looking for pictures of dogs or cats or elephants, and you could be looking at images and be able to do that sort of thing with a classification model. In addition, if you're looking at people's looking for credit scoring, that you could be looking at other data, more maybe tabular data, like information about credit rating, credit history, and that sort of thing, that'll help us understand more about that information. Segmentation models are an interesting approach to looking at things. That it is, how do you look at all of the data and then separate every portion of the data out? So for example, in healthcare, we could be like trying to actually identify a tumor within a 3D image. Another place you would be using segmentation would be in the automotive industry. For example, if you have a self-driving car and you've got a camera looking forward, I want to know what is a road sign. I want to know what the road is. I want to know what a person is. I want to know when it's a building or a tree or something else. And each pixel of that image can then be labeled on its own as a road, as a tree, as a person, that sort of thing. Moving on, we could look at, what's the likelihood of an outcome prediction. A prediction isn't just a DL task, but it's also an ML task about, given the information, what can we understand? From healthcare perspective, one thing that's been done was a really interesting study from the child healthcare in LA hospitals, was to look at the health metrics of children in the ICU and understand what is going on with their healthcare and what's going on with their state, and can they figure something out ahead of time that maybe a human wouldn't detect by looking at all the time history of all of the information they have from that patient, and see if they can do something more useful and more proactive than waiting for their state to change before doing things. Fraud detection is from the finance is also really important as well. We all appreciate that on our credit cards. We want to know ahead of time if someone's accessed our credit cards or used them illegally or inappropriately, and get that and do that fraud in real time. When we're talking about recommendations, this could be something when you're, watching movies with Netflix. Hey, when it says, maybe you would like to see this movie, that's what they're doing. Whether this is in trading, whether this is in shopping, whether this is in therapy recommendations, these are the different types of tasks that could be mapped from questions in the business side to the types of algorithms that are out there today. And this is a subset of these questions. We don't have time to go through all the variations. We're trying to hit the most prevalent ones we're seeing in business today, but we could spend another hour or two talking about all the other options that you would have in this. So I want to kind of go through from the perspective of training models and inference of models, deploying to models in the ML and DL space. So this is kind of focused on those two things that Brien referred to. He talked about, looking at all your raw data and scrubbing it and cleansing it and trying to make it prepare it. That's where you have your data set training. This is what I want to use to try and create a model to do one of those things that I just discussed. And then from there, we're going to have this untrained model. There's one of the things about the models is it is a complex field of understanding how you take different types of models or different model architectures and apply it to a problem. We're not going to address that here today, But the nice thing is that within the academic community, and even within the business community, a lot of this has been done as open source. So when all those options, all those examples I gave on the last slide, that you can go off and download these things pretty much from GitHub, from research papers and that sort of thing, such that you have somewhere to start. You may have an untrained model, but you don't have to be starting from first principles about how would I create a model. So it's really helping adoption of these technologies, that all these tools are already out there. And then I just have to get my data set and then train against the model. So from this, we're going to implement this untrained model in some sort of deep learning framework. These typically come in Python, but there's others that can be done with Java and other languages as well. And what we're trying to do is just take that data set and push it through the model and use the weights to combine them and figure out, hey, in this case, we're just trying to train, hey, is it a dog or a cat? And it's going to do this set of mathematical operations. It's going to get to the end and say it's a dog or a cat. But what goes on with training is that it gets to the end and it predicts something, but the training data set usually has labels, and the label says that I'm a cat, but I might have predicted that I'm a dog because the model is untrained. And so then what happens is it uses that difference, whatever's at the end of the difference, and then it propagates the errors back to the beginning, updates all the weights and does it again. So it's a very iterative problem where you go through all of the data, but then you also go through the data many, many times to try and converge on the best solution. And so, going to one of the questions we already had is what kind of IO patterns are we going to see? From the ML and DL application developed from training, the dominant read IO pattern here is actually reread. And I want to say reread for a specific reason. Yes, it is primarily a read operation, but since we're going to be rereading the data, the full data set 40, 50, maybe even 100 times, that the key is how do you reread the data? And this is going to go back to data tiering and caching. How do we keep the data as close as we can to the compute units such that I don't have to be going back out to storage to do these things? If you're staging all your data locally, hey, great, you're probably already local, you're taking care of it. But when you have clusters of systems doing training, whether you're going to be training problems, across multiple nodes, or you're just going to be having multiple nodes working on the same problem, or you're having multiple nodes on different problems, we typically see some sort of shared file system at this point of high performance, such that IO is not the bottleneck. So you can always go back to disk and the file system and read all that information, but that's may be expensive. The mechanics of shared file systems is complex. There's reasons why we want to have larger objects versus smaller objects when we're reading. When I say objects, I'm not necessarily saying S3 type objects. I'm just saying your data set size, like smaller images versus larger images, or pieces of text versus whole sentences. The larger the data we can read is always beneficial to file systems and storage in general. And so we're going to reread this over and over. So in this aspect of training, back to the question, what's the read-write mixture? The read-write mixture, I would go often is more of 95 to 5, 98 to 2. I mean, it is very read dominant, but the key also is that there's a reread component, and how can we keep the data closest to the compute systems as we're using it? The reason I say there is a little bit of a write component is because generally during these trainings, this training might take hours, it might take days to accomplish. And we want to be saving checkpoints along the way, so we have a state of the system so we can evaluate it in the future, but also in the event of an interruption of the training, that we can restart the training from that checkpoint, not have to go to the beginning. And so sometimes these checkpoints are very small and it's not very heavyweight. Sometimes these checkpoints can be very large. If we start talking about some of the natural language processing tasks we hear about today, if you've ever heard of GPT-3, that if we're using the very largest models out there today, that checkpoint data that needs to be written could be on the order of hundreds of gigabytes or terabytes. And you want to do that as fast as possible to not waste time and not be able to continue compute. So that can be a big problem on its own. Now that is talking about the very high end, but that's where some of the ideas are going today. So after we have this new capability, what do we do with it? Well, we want to use it for something. Like, for example, if I want to be able to ask my phone a question that I want to say, when is the next showing of the next James Bond movie? I would like it to give me an answer. And so that part is inference. It is much more, it's lightweight. It only does this training part, but it's a mathematical evaluation going forward, not the complexities of going backwards and iterating. You just do it one time. And so you take this new capability, you deploy it somewhere, and then you can optimize it for performance. And then you're deploying this somewhere, and then now you're taking new data in and going through and using that. So Data can come from a lot of different places. You could be doing more real-time online things where I'm just talking to my phone, or you're on a website with a chat bot and that sort of thing. You could also be looking at data offline. You could be going back through and say, hey, I have a mapping application and I have all this different data that I've collected from satellites or cars driving around or something like that. And I want to look at all that data again because I want to know more about that than the last time I used it, in that iterative nature that Brien talked about of improving the model over time. So either way,
For the moment, we appear to have lost our audio. Not sure where that is. We're trying to figure that out right now. Please bear with us
hey, Tom, when did you lose me?
How
long
about
did
a
you lose
minute
me?
ago.
Okay. I think I'll just go back to inference really quickly. Inference is the forward pass of the data. It can be data intensive if you're working with offline data and you are reprocessing data, or you could be, maybe less stress on the IO system, on the storage system when you're bringing data in online from like web clients and that sort of thing. And lastly, what I wanted to address was that in terms of data set size from the previous question, is that we could have cases where data sets are gigabytes or even terabytes or petabytes. It is really going to depend on your applications. What we see often today, from my experiences, has been really in the tens to hundreds of gigabytes, but I hear examples in the terabytes or even petabytes. But it is going to depend on your data set size, and data set size also is a function of model complexity. The more complex the model is, the more data that it can ingest and do something accurately with. So sorry about getting cut off in the middle of that. I hope I didn't lose any messaging. And I think we are ready to move on, Tom.
Ready.
Tom, I think you're muted.
Uh-oh.
There we go. Gotcha.
Oh, you told me I was unmuted, but whatever. We're there now. Okay, so we have a couple of questions already on this. Brien, as you were talking about the risks of dealing with OLTP databases, in online state, you talked about some risks, and there's a question. They want to know more about these risks.
Right. Actually, it was Young who was mentioning, but I can talk to it a little bit.
Okay, my apologies.
Yeah, no worries. Particularly with OLT databases, you may need to either clone it, because what you're dealing with is a database that is doing a high transaction volume. So in that particular case, you may want to either clone it, or the system may be fast enough to deal with it, but you're going to have to look at that inference, because inference is something that's going to be running, right? You're going to have a number of data coming in from your users. You're going to have data coming in from thermostats or drones, or photos coming in, videos coming in. Whatever that data is coming in, it's moving very quickly, right? And you need to test to make sure that your environment can handle that. And this is kind of part of the testing of the system, kind of stress testing of the system when you first put it in line. And so there are ways of mitigating it, like I mentioned, cloning and other ways. But if your system is fast enough, you might be able to handle it. Things to be aware of is sometimes you go from one resolution set of cameras to a higher resolution. Just that little bit is enough to significantly change your overall dynamic. So you have to be aware of it. And that's an area where things like monitoring and automation really help you to catch things like jitter and other things that are coming through in your environment.
Mm-hmm. So, and I can add to what I was saying, basically. So I've been involved in a use case in fraud prevention. And the major issue there is that the OLTP database is the actual financial transaction that somebody wanted, a transfer of funds or something along those lines. And the major question for the people doing the AI is, how soon do I need to get my model trained? So if you have transactions coming in and you can wait until that night to do an extract of the data and then begin to do your training, then the next day maybe you'll have a model that knows how to deal with fraud prevention. The problem is it's fraud prevention. So the more time that a bad guy has a chance to commit that fraud, the worse they are, worse off they are. So as short a time as possible between the time that a fraud is committed and the time that they've learned how to detect this is what they're looking for. So the problem, of course, is if you're trying to read from an OLTP database that's actually doing a financial transaction, and you put so much stress on it that it can't do the transaction, that's also not desirable either. So this is one of those cases where you have to be very careful about your design. You can tee off your transactions, or there are a number of different techniques to do this, but it is very imperative that the people designing the system understand the feedback that's going on. How fast does it have to occur in order for their system to be kind of responsive?
So, Young, let me add one more thing to that, just in general, as it relates to deep learning, machine learning training, is that there are times where you want to be able to reproduce those results. You're going to want to be able to go back and whether this is, there could be some legality issues for the example that you just provided. This could be automotive in a sense of like, oh, I had a car crash. We have to go back to see what the models did. By taking a snapshot and then training off of that means I have that data. If the OLT database is live and then a new transaction comes in, I can never reproduce the model I had the first time. So from data provenance itself, there's probably a reason why you want to be taking those snapshots so that you can track what you've done and be able to reproduce that in the future if it becomes important.
Yeah.
Right.
In talking about data and data types, question comes in, do we have to normalize that data to the same type? Or can a model accommodate different data types?
So it depends on what you're doing. Generally with images, you'll want to do a degree of normalization, right? Because you've got some images with very low resolution and some with very high resolution, it can very much throw off your model. But it depends on the type of data that you're working with, and some models tend to be more forgiving than other models.
Yeah, I've heard of cases where somebody was doing medical image recognition, and the problem was that when they trained the system, they trained it on one hospital's data, and then they transferred it over to a different hospital system. And because the contrast was different, the results they got back were terrible. So it is very important to understand when you do and don't need to renormalize your data.
Great.
As terms of data types, there are models that could actually use multiple data types. So it like, for example, if I wanted to create a model that if I gave it a picture, instead of saying there's a cat or a dog, try and describe the picture like I see a cat playing with a ball on a table. Well, then you would have input of both text and the images, and the text and the images would be paired together such that you could train a model that way. And then in the end, you could feed it a picture and inference, and then it would give you back the text. So there is always a sense of normalization, but there are examples where you may use just completely different data types to function as in one type of model.
So are storage solutions that are right for one form of AI also the best for others?
No.
Yeah.
I mean, so this is, coming from more of an infrastructure background. You need to look at what your particular environment is doing. Like you said, you've got fraud detection where you're trying to do things that are near real time, or trades and transactions in the financial services industry. And then you've got others where you're doing large batch, some where you're doing very large jobs, some very small. Unfortunately, this is the reason why you have trained storage professionals, because you're going to look at the data, you're going to look at how the IO patterns of the particular set of algorithms that are being run, and you're going to help tune that environment, and you're going to help your team make it successful.
Mm-hmm. Yeah, and I've seen I mean, just two kind of quick examples, right? There are people doing images. Images are generally on the order of megabytes or larger. And there are people doing like things like recommenders, where the data set is quite small, maybe on the order of a kilobyte or less. And just the act of trying to create some data resiliency around this is very challenging. With a large image, I can take it, I can break it up and do erasure coding on it, and use that as my way of protecting my data from the failure of one device. I cannot do that with you know, 1 kilobyte object. It's just too small. So there are different ways of handling that sort of data security, and I've seen everything under the sun for an AI system. So it will depend on the use case and a lot of things around this, but these are the things you have to think about.
And some of that is also, what's the value of your data? Where can I put it for safekeeping, and can I reproduce it? Sometimes reproducing data is easier than storing it. Sometimes I can't reproduce it. You know, if I'm collecting data from hundreds of cars driving around trying to collect information for autonomous vehicles, certainly that data has a lot of value. Then you have to ask the question of, where do you store it and how do you store it? And, you know, what sort of in our tiering mechanisms do we trade off resiliency of the storage versus performance of the storage, and why we may move data from one tier to another in terms of when we want to use it. So it is a complex question.
Yeah, and one thing that we definitely see on the edge, people who are doing AI on the edge, is yeah, you're saving all of the data for a day, 2 days, 3 days at that individual site, but you're going to basically aggregate up the thing that's going to get stored long term is going to be, you know, what was the temperature on the minute, on the 5 minutes, right? Because that's enough for long term analysis. But where you're looking at the thermals on a particular machine or a drone or whatever, you want it by, you know, at the millisecond level that it's actually being captured. But in a longer term view, and what's getting sent up to the data center long term, right? So you did the inference on what exactly is going on, and then longer term, you're basically sending a much smaller data set up to your database, right? And you need to make the determination of how much of that data you care about, but you know, the time increments are much more granular as it goes back to the data center, so that you're conserving space.
That all makes sense. How do features like CPU bypass impact performance to storage?
Let me start there. When we're talking about some of the larger high-end models, certainly in computer vision, we are seeing examples today where people need to read data at gigabytes per second per server. And that can scale up as you add more and more servers. And when I say gigabytes per server, I've seen 3 gigabytes per second, I've seen 20 gigabytes per second. And as technology gets faster, we're going to expect to see faster ingest rates. And so being able to get that data to where it needs to be is more important. That these are very computationally intensive problems, and we want to avoid going through portions of the computer that we don't need to do. And so some of those ideas of bypass are becoming very important, as we're like, we know where the storage is, we know where the networking card is, or even if it's a local disk, why do I have to go through the CPU if I'm going to some sort of accelerator? We should be able to put that data right in there. And what it does is it's providing a faster path to where the data needs to be processed, but it's also eliminating other components that could be off doing other things that don't need to be just bypassing, you know, passing data through and funneling it through when those resources are precious. So it's becoming more and more important at scale. It's becoming more important for these applications. And so I think we're going to see a lot more of that in the future as data sizes and data types continue to get larger.
I definitely agree with that. One of the things that we have been taking a look at Samsung is that we knew for a long time, when you put like anywhere from 4 to 6 SSDs onto a single host, you're likely going to saturate the CPU. And that's kind of a problem for us, right? So we have been taking a look at new designs. How do you get more SSDs onto a host, but still be able to extract the performance out? And it turns out that one of the major bottlenecks is the memory between the CPU and its local DRAM. As you're copying that data from the SSD in to the CPU, you have to sometimes make multiple copies of the data before sending it out to the network. So this is on the storage server. And so we've started experimenting and taking a look at, the requests will come in, however they come in, the CPU will have to handle it. But once the responses go out on the storage server side, we can actually also do a CPU bypass, hand it over to a NIC to go over the wire. On the other side, there's another CPU bypass that's possible, not necessarily required or desirable. But these, I think, are very, very important technologies to get us to much better scalability of performance.
Right. And from our perspective, what we're trying to do is make sure that your data gets to where it needs to be as quickly and efficiently as possible. With every generation, we increase the overall speeds and feeds for each of the environments, and we're aware of kind of what's going on in the AI world, and are trying to make sure that we have the capabilities to offload what needs to get offloaded and process quickly what needs to get processed.
There's a related technology that's been recently promoted within SNIA called computational storage. How does that play in terms of both inference and deep/machine learning?
Ooh, that's a tough question. What I can say is that computational storage definitely has some at least theoretical pluses. So one of the things that you could in theory do is the normalization that we talked about before of the data. So you read an image off, and the normalization could be transferred over onto the GPU server to do the training, or it could be kind of left on the drive. And how do you choose to do this? So for me, when you're dealing with AI machine learning, you have to be very cognizant of what parts of your training must be or can be parallelized, and what kind of needs to be done on the fewest number of nodes possible. If you can do that, then you have a hope of understanding what role computational storage has in your environment.
Yeah, I think any way we can put more compute at the problem and isolate it to its specifics is a useful thing. It's not exactly computational storage, but when you look at the data processing unit, where we can start to put that, maybe not on the compute side, but somewhere else in the middle of the pipeline. Can we add more cycles somewhere in the middle of the pipeline that can do the normalization, can do the pre-processing, can offload functionality, so that the traditional the CPU can do things it's best at. As we can offload those things, then we can provide more. We're eliminating bottlenecks. We're ultimately providing more performance and finding ways to move technology and move applications forward in a world where we certainly don't have a single computational unit.
Right. And for computational storage, Intel looks at it as a way of getting the data that much closer that we're working on to be able to do whether it be big data or AI workloads. Having that data readily available. We talked a little bit about caching, having the data that you're working on, that you're doing multiple reads on there, so that the system isn't having to go get it off of other systems in whatever manner that you have it stored, block or otherwise.
Is a CPU bypass device, is that the same thing as a smart NIC? So, or does it encompass more than that?
So you have protocols, right, like RDMA and other ways of doing bypass. RDMA allows for the drive, right, on one system to literally get a request for data, send it directly to another system in your environment. Things you want to be aware of is, like, you really need to be close to it. So generally it's a top of rack environment, so that you're accessing another system that's directly in the rack, very latency sensitive. But yeah, and it's going to be able to access directly to things like GPUs, things like other CPUs in the environment. It's a really neat technology, and it's a way not to have storage be bound up on one system, waiting because somebody's got a big job on that system. You can access that storage directly and get the answer that you need faster.
Right. I think The smart NIC is kind of a generic term. I don't think there's an industry standard, but exactly what Brien was saying, RDMA is a part of the smart NIC technology, and at NVIDIA we're trying to work to make the NICs smarter, as a drive to offload processes, and certainly for storage, and having this our parallel shared file systems be mounted at the NIC level, and then processing that within the server, providing actually better performance and better security, and removing load from there. I think we're going to see a lot of places where, quote unquote, smart NIC is going to be a lot smarter in the future as we dedicate CPUs to do what they're best at and find ways to offload those tasks to offload other tasks to devices that are more appropriate.
Yeah, I would definitely agree. One of the things that I've seen is that I would say the smart NIC is probably the first major use of a CPU bypass, but it's far from the only one. So it's possible to put a device in a server, have it access SSDs directly without going through the host. And again, what that saves you from is having the CPU do things it's maybe not the best at, and it will save on the memory bandwidth as well, leaving the CPU to do what it does best. So I'm definitely not saying don't use the CPU. It's really good for certain things, and it makes programming a lot easier. But there are definitely use cases where it doesn't need to be there, or maybe it's just not as efficient at handling certain things like block operations or things like that.
Sure. So in cases, say, a Rocky V2 system, where the NIC sees that the request come in, it can make that request directly to the local NVMe drive, which would then transfer not through CPU memory, but then straight back into the NIC's memory bank, and completely bypass the CPU and save bandwidth to local DRAM. These are the kinds of things you're thinking of?
They are. I mean, there's a lot of new technologies that are coming out right now that are looking at ways of juggling resources, right? You always have kind of compute, network, and I/O, and one of them is always the bottleneck, and what it is, it's a matter of balancing, right? It's trying to figure out where the best balance is for the workload that you're trying to do, and with AI, the faster you can move that through, because one of the things we didn't talk about with AI is you're not generally doing one thing in AI, right? You're going to do one thing. You're going to do the object detection, and then you're going to do something with that object detection. You're going to find the fraud, and then you're going to want to act on the fraud. So you're actually generally with AI setting up a series of actions to happen, and the more that you're doing, right, the more compute you're leveraging, whether it be additional processors, the storage, or the CPU, right? So what we're doing is we're making business more capable, and we're allowing these smart systems to do more and to be more capable.
Okay.
I think also in this is just looking at where we're going. If you have a 100 gig Ethernet, you've got EDR InfiniBand. Okay, that's fast, but the local memory can keep up with it. And yeah, you'll be using the CPU and the memory inefficiently, but because you don't need it, you could bypass, but that's one thing. But as we start to look at applications like users and customers who are saying, I need to push 40 gigabytes per second into the server and process that all at one time, or 100 gigabytes per second. When you start to talk about these numbers, it's not just that we want to avoid local RAM because it's just getting in the way. It's just, you can't keep up. Like we're going to start, even though DRAM is supposed to be really, really fast, when we start talking about 40, 100 gigabytes per second into a node to ingest and process in real time, or then those things are just going to slow everything down. So bypass becomes not just a nice thing for efficiency, it's a requirement to even match the goals of what your customer wants to do.
What work is being done to accelerate S3 performance for use in AI?
So that's a very interesting question.
And please, let's genericize this to something more than just Amazon for those who are using other styles.
So for those of you that may not be familiar, S3 is a protocol kind of created and popularized by Amazon. It's a great interface for transferring objects over standard TCP. I would say one of its biggest limitations is it relies on HTTP and TCP. And so all of the discussion we had about RDMA is out the window right now. That's one big factor in all of this. File, on the other hand, for a long time, you've been able to do file over RDMA. There are protocols for doing that. So we already have those advantages. So this is one of the things that we really have to pay close attention to, is the fact that file is very good at transferring data at high performance in relatively smaller quantities. If we're talking about a few petabytes, file is fine. When we start taking a look at very large data sets, and I have a customer, or actually multiple customers, looking at hundreds of petabytes, file becomes a little bit of a liability, and you need to start looking at object in terms of how to transfer that data. But then how do you enable GPU direct storage, for instance, or any sort of CPU bypass? It becomes much more challenging. So those are things that we're definitely looking at and need to figure out how to make these changes. And I do also want to say that our initial thinking was a lot of that is more on the hardware side, but there's some software issues as well. If you take a library that's used to POSIX file standards and you say, well, let me put this translator in place and I'll translate over to S3, it can work, but sometimes there'll be very, very bad side effects. A simple example of this is if I take a file and I want to rename it. In POSIX, it's very quick and easy, right? You don't actually move the data in order to do that. In S3, that's actually not such a big, that's not a simple thing. If you rename an object, it may have to make a full copy of that object all over again. And so it will technically work, but the side effects may make it unusable.
Yeah, I think going back to when I was talking about the reread capability that's important, the way that we were looking at architecting solutions today, given what Young had said about the pros and cons of S3 or object style storage, is that we would have some sort of file-based solution that is closer to the compute, and S3 would be more of the cold storage. And so we'd certainly be looking for technologies that automatically stage data that will bring it to that local file that's going to be faster. And even if we're rereading from that, that is certainly better than going off and trying to reread from the S3 or the object store to be able to do the training.
Yeah, and for Intel, we work with a lot of the different open source projects and leverage technologies like our ISA-L to create accelerators to be able to bring that data in as fast and efficiently as possible. Get it to your applications that need that data. Our goal is just to try to accelerate that as much as possible, and then where possible, get it to other file systems as quickly as possible.
So will storage for AI ML necessarily be different from today's standard enterprise storage systems? It's kind of loaded, I know.
It's a loaded question. I would say that at least short term, we're likely to continue using the enterprise type solutions. But I know that as I've taken a look at again a few customers, but these are big scale ones, in their large scale solutions, they're just not finding anything that enterprises have been able to use and deal with today. So short term and maybe medium term, it will probably continue using more traditional storage solutions. Longer term, we'll have to take a look, and maybe only the largest ones will need something significantly different.
I know it's a loaded question because what's the definition of enterprise? One thing NVIDIA has been looking at is for the performance numbers that I've been quoting today, that if we're talking enterprise style NFS network attached storage solutions, they sometimes can't meet those sorts of requirements. And so we have been looking at more things that, this is where the enterprise definition gets a little fuzzy. What about parallel file systems? What about file systems that aren't based on NFS? They have their own protocols, traditionally coming from other architectures where we want to be able to distribute objects in parallel and perform and achieve these great performance numbers. So if you want to define those as enterprise, then I'll completely agree with you, Young. If not, we are looking at other technologies that are meant to be deployed in the enterprise, but not as traditionally accepted.
Right.
Ones that come more from high performance computing, and I apologize for saying that. I was trying to avoid that term for the group, but it is true. So we are looking at other technologies like that to improve performance and real good scalability for capacity before you have to move to an S3 style or object style solution.
Yeah, I mean, we're working both on the hardware side and then also with a lot of the open source projects to see what else is possible, right? To try to take the object stores and make them faster and more efficient, because I think everyone sees that file is great, but the tree depths once you start getting to multiple petabytes up into the exabytes just don't work. So yeah, I mean, it's an interesting time, and I think that there's a lot of possibility out there, and at the rate things are changing in AI, I think that for now we're using the systems we have, but I think there's a lot of a really bright future for some of the newer technologies that are out there.
Well, I thank all of you for the time that you've spent in researching and presenting today. And let's go back to the final slide. So as we end this talk, please, before you leave, rate us on how we did with this webcast. Give us your feedback. Give us any other questions that weren't answered, and we'll make certain to get that all up. The slides are available immediately. If you go to the attachment tab, you can download that before this ends, and you'll have the slides. Otherwise, you can find it here on this link. And in our blog, we'll be putting up all of the questions today, as well as any additional ones. Follow us on Twitter, and thank you so much for being here.
Thank you.
Thank you.
Thank you.